Curvature is a measure of, for lack of a better word, how bendy a function is at any particular point. If a curve has a place where the direction changes rather quickly, then that would be referred to as a place where the curve has large curvature. And for straighter portions of the curve, we would call those having small curvature. A way to characterize how the direction is changing is to consider the unit tangent vector. The unit tangent vector has a magnitude of 1. And so if a unit tangent vector is going to change at all, it's going to change in its direction. And in areas of large curvature, the unit tangent vector changes direction rather quickly. On areas of small curvature, the unit tangent vector doesn't change direction very much, and maybe not even at all. This idea leads us to a definition of curvature. It's denoted using the Greek letter kappa. It looks like an uppercase K, but it's not. It's the Greek letter kappa. And it is equal to the magnitude of the derivative of the unit tangent vector with respect to arc length. So I'm going to denote that this is by definition. We're going to have a series of equal signs here in just a moment. This dt ds in magnitude is, as I just said, how the direction of the unit tangent changes. Did I say vector? I meant to say the unit tangent vector changes along the curve. And while that definition is helpful to conceptualize what is meant by curvature and how folks have come to quantify such a thing, that's not how we're actually going to compute it. We're going to compute it using one of three formulas. The magnitude of t prime of t divided by the magnitude of r prime of t. I will call that expression number 1. The second one would be the magnitude of r prime of t cross r double prime of t divided by r prime of t in magnitude cubed. I'm going to call that expression number 2. The third expression applies to a special case. For a plane curve in R2, that is, if we have y as a function of x, then kappa is a function of x as well, and is equal to the absolute value of the second derivative of f divided by 1 plus f prime of x squared, the quantity to the 3/2 power. I will call that expression number 3. And while we have the definition of the magnitude of dt ds, these three expressions are how we're actually going to compute it. As for which expression to use, between 1 and 2, it's really just a matter of which one do you prefer to use. Do I want to find the derivative of the unit tangent vector, or do I want to find r prime and cross it with r double prime? For the third one, it's pretty well laid out. This is if y is a function of x. Now let's see how the definition leads to these expressions that we're looking at. We'll start with number 1. To develop it, we're going to start with the derivative of the unit tangent vector with respect to time. So dt dt, where the first t is the unit tangent vector and the second t is the parameter t. That's equal to dt ds times ds dt, where again the first t is the unit tangent vector, the second t is the parameter. This is true by the chain rule. We can solve for dt ds by dividing both sides by ds dt. And so we get that dt ds, that's the unit tangent vector, is equal to dt dt divided by ds dt, which means that the magnitude of dt ds, the derivative of the unit tangent vector with respect to arc length, is equal to the magnitude of dt dt divided by ds dt. dt ds is what we were told initially is what kappa is. So kappa of t on the left-hand side. And on the right-hand side, within the magnitude in the numerator, we have dt dt, the derivative of the unit tangent vector with respect to t. That is t prime of t in magnitude divided by ds dt, which we saw in a previous video, is the magnitude of r prime of t. And so that shows where the first expression comes from.